Welcome back everybody to another video lecture from Miss Semino. Tonight we're going to be talking about thermochemistry, and this is video number 1 in the series. This first lecture is probably the most important out of all of the ones because this gives you the basics of thermochemistry. So some of the things that we're going to talk about tonight are how energy, heat, and work are related. We're going to talk about exothermic and endothermic reactions. We're also going to use graphs to help us do that. We're also going to identify the units that are used to measure heat transfer, and we're going to talk about these two terms, heat capacity and specific heat capacity. So sometimes this one's called specific heat. You definitely need to know the difference between these two terms. So the first thing we want to do here is define thermochemistry. So you'll be shocked to find out that thermochemistry deals with the heat changes that occur during chemical reactions. Since we're talking about heat, we're going to be talking about energy, and so the formal definition that we're going to use for energy here is the capacity for doing work or supplying heat. Some things to know about energy: weightless, odorless, tasteless, and if it's in a chemical substance, we're going to talk about it having chemical potential energy, so we like to talk about that being stored in bonds a lot in chemistry. So an example of a chemical that will contain a lot of energy is gasoline. So we know we use that to power our cars and other vehicles. Heat is represented by the letter Q. This is going to be important. You're going to want to remember that. And is energy that is transferred from one object to another because of the temperature difference between them. So you want to know that heat changes can only be detected, so we can't actually see like how much heat is. We're just looking at the changes. And of course, shockingly again, that heat flows from the warmer to the cooler objects. Sometimes I see kids say, well, it got colder, like the cold was transferred. No, remember, heat is what's being transferred. So this slide is very boldly trying to tell you that essentially all chemical reactions and changes in physical state involve either a release of heat or an absorption of heat. When we describe the absorption or release of heat, we're going to talk about them being as exothermic or endothermic. You're probably familiar that exothermic, you're releasing heat, endothermic, you're taking in heat. But now we have a few more terms. We need to be a little more specific about what's going on. So we use these two parts when we're defining these words. So the first one is the system. It's the part of the universe on which you focus your attention. I like to talk about like this is exactly where the chemical reaction's happening. And the surroundings include everything else in the universe. So the system really is like that chemical reaction, and this might be like the air or the water or the container surrounding that chemical reaction. So when you add your system and your surroundings together, you're going to make a universe, or at least it's called a universe. That's how we describe that. And so thermochemistry is concerned with the flow of heat from the system to its surroundings and vice versa. So let's just quickly review the law of conservation of energy, and it states that in any chemical or physical process, energy is neither created nor destroyed. So all the energy in the system and the surroundings can be accounted for as work, stored energy, like that potential energy in those chemical bonds, or as heat. So we have talked about endothermic and exothermic reactions before. So when we talk about endothermic reactions, we're going to see that heat is flowing into the system from its surroundings. So you can kind of see like, okay, so here's the surroundings. Remember, it's everything outside the system. So heat is flowing in here. So remember, we only can measure the change in heat. So our Q value, okay, so if this is our Q value here, we're going to have a positive value because heat is flowing into the system. So it's going to be more heat. So it's going to be positive. And so the system gains heat. It gets warmer as the surroundings would then cool down. Because remember, for transferring heat from one thing to the other, this one out here, it will have to get colder. And then you'll be, again, I feel like this lecture is like a whole surprises for you. I'm hoping you're hearing the sarcasm there. That if we have an exothermic reaction, heat is flowing out of the system into the surroundings. So if you're losing heat, that Q value is going to be negative, and so the system loses heat, which means the system gets cooler and the surroundings heat up. So here, let's just go ahead and review that every reaction has an energy change associated with it. Exothermic reactions release energy, usually in the form of heat. Endothermic reactions absorb energy, and energy is stored in bonds between atoms. We knew that potential energy that was being stored there. So this is that second or third objective that we had for this lecture. We need to figure out what the units that we're using when we're measuring heat flow. So we usually use this calorie, and it is defined as the quantity of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. Now this is a pretty important definition. You're going to want to go ahead and memorize it. Also that it's 1 gram of pure water being raised by 1 degree Celsius. And so this calorie here, do you see how it has like the lowercase c? So you'll sometimes see this uppercase c when you're talking about food energy. So 1 calorie with the capital C, like 1 calorie that's in your food, okay, or your food package, you'll see it on there, is actually really 1 kilocalorie, which means it's equal to 1,000 calories. I think they're trying to not make us feel so bad. When we eat something that's 300 calories, it's really 3,000 calories. So it's enough energy, again, in that case, to raise 3,000 grams of pure water by 1 degree Celsius. Another unit that we will see in this unit, or this chapter, let me say it that way, is called the joule. So the calorie is also related to the joule, the SI unit of heat and energy. So it's named after this guy. And here's our conversion factor that you're definitely going to want to know. So that 1 calorie is equal to 4.184 joules. So now, here is our third objective. We need to talk about heat capacity and specific heat. So our heat capacity is the amount of energy, the amount of heat needed to increase the temperature of an object by exactly 1 degree Celsius. So again, another definition to kind of remember. Okay, so the amount of heat needed to increase the temperature of an object by 1 degree Celsius. This depends on both the object's mass and the chemical composition. So it's not like we have a specific mass or a specific composition we're looking at. It's just generally described here. Now, the specific heat capacity is more specific in its definition. It is the amount of heat that it takes to raise the temperature of 1 gram of the substance by 1 degree Celsius. So if we were to look back at that previous slide, remember it didn't matter how much of the substance we had. It was still 1 degree, but it could be, just different masses. So often we'll call specific heat capacity just the specific heat, and you'll hear me refer to that in class. If you look in your textbook, you'll see some reference materials, or on our worksheets we'll have them. So one important aspect to talk about when we're talking about the specific heat capacity is water's specific heat capacity. It actually has like a gigantic value when compared to other chemicals. So we're going to talk about like why this makes water such a great thing. It absorbs heat, why it's maybe like the solvent of life. We'll talk about some advantages of using water. So here is a chart that describes the specific heat of some common substances. On the last slide we were talking about how water has such a high specific heat, so notice this value is much larger than these other values. Also notice, I remember thinking that this was interesting, that if you look, you've got liquid, solid, gas here. So all of these are water, but it depends what the specific heat is depending on the phase. So if you remember back to our phase diagram where we were going our heat curve, that line for when you're going from the liquid to the gas was really long, and that's because you had to add lots of energy to it before it changed to the gas phase. So remember, we've got all of these hydrogen bonds working here. Speaking of hydrogen bonds, look at ammonia here, NH3. It also has a pretty high specific heat because of those hydrogen bonds. So then if we look down here, like the big comparison is to look at these metals down here. And so what I want you guys to think about is if you ever put a pot of water on the stove, so your pot of water is there, and the pot is made out of metal. If you set it on the stove for a minute, after a minute that pot is actually really hot to touch, like the metal pot itself, but you could probably stick your finger in the water. I don't suggest trying this, but you'll notice that the water hasn't really increased in value, so that's a good example of the specific heat differences in these substances. The metal pot is super hot after a minute, but the water really doesn't feel like it's changed its temperature hardly at all. So some values that you want to be aware of, that the heat capacity and specific heat of water is our C value, or our specific heat, is 4.18 joules. Sometimes you'll see a few more digits in this 1.8 here, like sometimes there's like a thousandths place in there. And 1 calorie for our specific heat. So you should know that this makes it water. It takes a long time to heat up, like we were mentioning, but it also does take a long time to cool off. And so that's why we can use water as a coolant, because it's not going to fluctuate in temperature very much, and it does take a lot of energy to heat up. Now we're finally getting to our equation for calculating specific heat. So remember that Q is our heat mass of our substance in grams. Our delta T is going to be our temperature change. Remember, delta means change in temperature. And then C here is going to be our specific heat. So we can find these units of either joules over grams times Celsius, or calories divided by grams times Celsius. So look out for either one of these units, and you can make the conversion factor if you need from the previous slide. And so finally, I know this slide is like a little hard to read, I'm sorry about that, but here is a sample problem for calculating the Q equals MC delta T. That's usually how I say that. So if we look here, it says the temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 40 degrees Celsius when the copper absorbs 849 joules of heat. What is the specific heat for copper? So in my brain, I'm thinking of that equation that we just talked about, and I usually say it just like this, you guys. So sorry, it's kind of like bad handwriting here. Q equals M. So this Q value is our heat, M is our mass, C is our specific heat, delta T. So this is kind of normally how I'll say this. So we're going to go ahead and do our knowns and our unknowns. So the mass, and they're just doing like a little CU here, is going to be the 95.4. Our temperature change, this is usually tricky for kids. Remember that it's your final temperature minus your initial temperature. So if we look up here, this is what it originally was, this is what it finally rose to. So then you just do a little math and you find that your temperature change was 23 degrees. They're telling you that the heat that was absorbed, and so we know that this is going to be a positive number, was 849 degrees, and the thing that we are looking for is that C value. So we go ahead and we rearrange the formula for C down here, so it'll be C equals Q over M times delta T. It's a little hard to see here. Let me see if I can move this slide up. Give me 1 second. There we go. I hope you can see that a little bit better. So now here's our stuff. We just go ahead and plug in those values. We do a little calculation, and we should be coming out with 0.387 joules over grams times Celsius, and this is going to be that specific heat capacity of that copper that we were looking for. Maybe you can go back a few slides and see if this is actually the same value that was on the previous slide. I hope that was helpful, you guys. If you have any questions, remember to write them down and ask me tomorrow in class. Good night.